Howdy! Welcome to Elementary Statistics. I am Lance Curtis, and this is the lecture for Section 10.4, Multiple Regression. Here in this lecture, we're going to look at multiple regression equations. So now, instead of having one variable that we plug into a regression equation, we're going to have more than one variable that we plug into the regression equation. This means there's a host of possibilities for making our regression equation, and there needs to be ways of determining which particular regression model is the one that we should be using. So we're going to look at multiple coefficients of determination and methodologies for comparing our multiple regression models and how to evaluate which one is the best one for making predictions. We'll also look at dummy variables and how to use those dummy variables. So if any of you are old enough to remember the days of CB radio, we could say, yeah, when you agree with somebody, say, well, it's a 10-4, good buddy. Well, yeah, we're going to get on with the lecture here. So it's a 10-4, good buddy. So, as I mentioned, this section in this lecture, we're going to look at a method for analyzing the linear relationship involving more than just two variables. So more than your x and your y. So we're going to focus on two key elements in this methodology. First, we're going to find the multiple regression equation, and then we're going to use values of adjusted r-squared and the p-value as measures of how well the multiple regression equation fits the sample data. Let's talk for a minute about multiple regression equations. Simply put, a multiple regression equation expresses a linear relationship between a response variable and two or more predictor variables. So the response variable is what comes out. It's the response to our predictor variable. So we're going to make predictions based on this variable, this variable, this variable, and this variable. We're going to put those into our model, our regression equation, and then the response is what we get out, and that's going to be the y value. The general form of the multiple regression equation is as you see here. So usually there's some coefficient that's all by its lonesome. And then we have for each of our predictor variables, x1, x2, so forth, there's a separate coefficient for each of those. Now, there's certain notation that we need to be aware of when working with multiple regression equations. As always, the lowercase letter n will be our sample size. Here, the lowercase letter k is the number of predictor variables. So the number of x variables that we have in our regression equation is going to be k. And then, of course, y hat is the predicted value for y. Let's look at an example where we're predicting the height of daughters based on the height of the father and the mother. So here we have a table of data listing the heights for a random sample of daughters along with their fathers and mothers. This data comes from the National Health and Nutrition Examination. Now, can we predict the height of the daughter given the height of the parents? Well, let's find out by making a multiple regression equation in which the response variable, which is the height of the daughter, in the predictor variables are the height of the mother and the height of the father. So we're going to take the height of the father and the mother, put them into our regression equation, which is our model, and then out comes the height of the daughter. Let's see if we can make one that reasonably predicts the height of the daughter given the height of the parents. We're going to use software to generate our regression equation. There are ways to do this manually, but it's super calculation intensive. So we're not even going to look at that. We're just going to look at using the software to generate our regression equation. We'll get into the details of how to do that a little later in the lecture. For right now, just walk with me on faith that this is the way it's done. So in your results window, there in StatCrunch, you'll get something that looks like this. So I can put in the values for the father and the mother and say I'm going to put these into the model, and what I want to come out is the daughter. And then here's my regression equation that you see there, parameter estimates table, a ANOVA table, and then a summary of fit. So our regression equation is listed here at the top. notice that we have this equation here. So let's look at each of the values in this equation so we understand what we're talking about. So D is the height of the daughter. That's the response that comes out of the model. F is the height of the father. M is the height of the mother. And then we have different coefficients. So there's an intercept value, which is a coefficient that doesn't have a variable associated with it. Then we have a coefficient for the father and a coefficient for the mother. Notice that these coefficients are the same ones listed in the parameter estimates table, just below the actual regression model in the results window. Notice I can get a p-value for the regression model, and I'm finding it here in my ANOVA table. So before we were looking at a model, a simple linear model, and it was okay for you to actually take the p-value from the parameter estimates table. Here, because we actually have more than one variable for our x value, you're not always going to see that match up there with the parameters estimates table. So you want to use the p-value from the ANOVA table if you're ever asked for the p-value, because this p-value takes into account the model as a whole, whereas the p-values that you see in the parameter estimates table are only looking at individual parameters of the model. So they're only looking at parts of the model. Furthermore, notice how the test statistic for the parameters is a t-score. So it comes from the t-distribution, whereas the test statistic for the ANOVA table is an f statistic. It comes from the f-distribution. So even though these p-values in this particular instance look to be the same, they're really not the same. This represents a two-tailed p-value looking at the t-distribution, with this being our critical value, 5.48, whereas here our p-value is a right-tailed p-value looking at to the right of this test statistic, 17.68, on the f-distribution. So even though it looks like the numbers are the same, and practically they are the same, but they're really not the same. They really are very different numbers because they're coming from different distributions. Look further at the so we have this p-value here. Remember, you don't want to use that p-value. Use the one from the ANOVA table. Now take a look at the bottom of our results. We have a summary of fit, and we've got, oh, hello, what's this? We have two r-squared values? Seriously? Two values? Oh my goodness, what's going on here? What's the deal with the two r-squared values? Let's take a look at that. So we have a multiple coefficient of determination, r-squared, which is a measure of how well the multiple regression equation fits the sample data. So if we had an r-squared value of 1, then that would be a perfect fit. Notice we're using a capital letter R here as opposed to a lowercase letter r. I think what your author is doing is using the lowercase letter r for a simple linear regression model, and a capital letter R or uppercase letter R for a multiple linear regression model. It can be a little confusing because in other sources, as I mentioned previously, the capital letter R is used regardless of how many variables you have in your equation. And really, I don't really see the value in making that distinction between a simple linear model and a multiple linear regression model. To me, it's like, it's a model. And however many variables it has is however many variables it has. Let's just find the model, figure out which one's the best one, and use it. Let's not get picky about, making little distinctions about, how many predictor variables do we have. But that's the course your author's on. I think that's why he's making that distinction. Anyway you slice it, here's your multiple coefficient of determination. So we're going to calculate it. As we saw in the previous lecture, the sum of the squares of the difference between our predicted value and the mean value, or the explained variation, and we have dividing that by the sum of the squares of the differences between the observed values and the mean value, which is the total variation. So the adjusted coefficient of determination is slightly different from this r-squared value because it takes into account how many variables you have and the size of your sample. So the calculation here is a little bit different. We actually have to get r-squared to calculate adjusted r-squared, but then we make this adjustment to it so that we can make an accounting for number of variables and sample sizes. The value of this multiple coefficient of determination is that it allows us to compare apples and oranges. So with just the r-squared value, you have to make sure that your sample sizes are the same and you've got the same number of variables in your model when you're comparing two models. With the adjusted r-squared value, you don't need to do that. You can have different sample sizes feeding your various models, and you can have different numbers of variables in each of those models. So this allows us to compare, for example, a model that has one variable with a model that has two variables or three variables or four variables, because the adjusted r-squared value takes into account those differences of the number of variables and the sample size, so that we can actually compare apples and oranges. That's going to come in really handy here, as we're going to see in a moment, because we're going to use this to actually compare multiple regression models. So when you're looking for the best, quote unquote best, notice the air quotes, multiple regression model, there's three factors that we're going to be looking at in particular. One, we're going to account for explained variation with adjusted r-squared. So there are a lot of people who use just a straight r-squared to judge model fit. But the problem with using r-squared is that its value changes with the number of variables and sample size. And the change is usually in the form of an increase in value. And so if you're judging a higher value to be more desirable, then what you get is sort of a weighted inflation for those models that have a larger number of variables in the model, or the data set is a larger sample size. And that may actually lead you to pick a model that's actually not the best one for your use. So you really want to use the adjusted r-squared value when comparing multiple regression models, because it provides a better accounting for the explained variation. It takes into account the number of variables in the sample size, so that we actually can compare apples and oranges on a more even playing field. The second factor we want to consider is the overall significance with the p-value. So generally, smaller p-values are more desirable. So smaller p-value, the more significant the combination of variables in your model. However, you never want to use a model with a high p-value measured relative to the p-values of all the other options. So one of the first things we do when we're comparing models is we look for the p-value and we say, okay, all you ones that have high p-values relative to the rest, we're just going to get rid of you from the start. That's typically a first step when comparing multiple regression models. The third factor we want to use is what's called sound judgment. This is something you only get from experience. So the more experience you have making models and comparing them, then the more judgment you gain in deciding, okay, what really is a better model to be using. Sometimes the model with the best numbers isn't always the best model. Sometimes a model with similar but slightly lower values can be the better model. You have to have a model that makes sense from both a creator and a user perspective. This is part of using sound judgment in selecting a model. Sometimes people who make models will actually make a model without any consideration for the end user. And you never want to be in that position, because it can come back to bite you. There was an example I remember from my days in industry, where a lot of design work for a particular portion of a power plant was being farmed out to China. Well, that's all good and dandy. I mean, outsourcing is the way the world's been working for some time now. But when they came to actually build that portion of the power plant, it was actually a housing so that you could keep pump equipment related to the generator away from the inclement weather. So it was just basically this little shack that you were building. But the problem that people here in North America had with those shacks was the doorway was way too short. And the reason the doorway was way too short is because the people who designed the doorway were Chinese, and they were thinking only of people who were like them. Chinese are, on average, much shorter than your average North American. So the doorway was a little bit short, and every time someone went into this little shack to check on the equipment or to resupply the oil or whatnot, do whatever maintenance needed to be done, they had to bend their head over. And while they're in the shack, they're bending over. It was really uncomfortable for them. And so it provided an unpleasant experience for the end user because the person designing it didn't consider the end user properly. And so you have to, the same principle applies when you're making models. You want to make a model that's easy for the end user to use and not something that's just convenient for you as the one who's creating the model. So, of course, you have to have something that makes sense from your end of it when you're creating the model, but you want to consider the user as well. So it's got to make sense from both sides of the coin and not just the one. Those tend to be the best models to be made. Let's look at our earlier example of shoe print length and height to illustrate what we've learned so far about multiple regression models. So sometimes in some of the problems that you have, you're not going to have to make any models. The models will actually be made for you and given to you in a table like you see here. So here we have a table listing predictor variables for different models under consideration, and there are corresponding adjusted R-squared values and p-values. So here we've got 5 different models. The first model uses only the age to make a prediction of the height. The second model uses only foot length to make a prediction of the height. The third model uses only shoe print length to make a prediction of the height. The fourth model uses foot length and shoe print length to make a prediction of the height. And the last model uses age, foot length, shoe print length, and shoe size to make our prediction for the model. So we've got 5 different models that we need to compare, and we need to figure out, okay, which one is the best one for us to be using? Well, typically we want higher values of adjusted R-squared and lower values of p-value. So first we can actually start by eliminating the first model. Its adjusted R-squared value is really low compared to the others, and its p-value is high compared to the others. Notice the p-value for most of these models is 0, but this has a p-value of 0.004. So we're just going to eliminate this one right from the start. Next, let's look at these last 2 models here. Notice that we have the higher adjusted R-squared values with these 2 models, but they also have more predictor variables with them. The p-values are the same, and the p-values here are not appreciably different from the other p-values that we see in the other models. These adjusted R-squared values, you could argue that they're not considerably different from these adjusted R-squared values here. So we're not really getting more bang for our buck. We're getting a little bit of an increase in adjusted R-squared, but not that much. So the added complexity to the model is not really worthwhile. It's not returning that much for the investment of work it takes to make that more complicated model. So therefore, we're just gonna say, no, we want a simpler model. So we're not getting that much value out of making the model more complicated. So let's just go ahead and eliminate these 2 models here. So now we're looking at two models that have one variable each in them, and they have the same p-value, but one has a higher adjusted r-squared value than the other. So we're actually going to look at those two models and say, yeah, we're going to take the one with the higher adjusted r-squared value because all the other considerations are the same. P-value is the same, number of variables in the model are the same. So we're going to just take the one that has the higher adjusted r-squared value, and that's going to be the model that we select. Now, it shouldn't be any surprise that we selected this model. The length of your foot provides the best predictor for the length of your shoe print. Well, duh. I mean, the shoe is made to go in the foot. So, of course, that's going to be our best predictor. It makes sense that this would be the model that we pick. Sometimes you're asked to evaluate different regression models, but you're not given that table to start with. If we look back at our previous example that we looked at with the height of a daughter being predicted from the height of the parents, we can illustrate this concept. So, looking back at the model that we made, the adjusted r-squared value is 0.637. That's not a really great value, but, you know, it's a decent value. Typically, you want to get above 80% to have a really good model, but 0.637, you know, it's not horrible. I mean, it's not great, but it's not horrible either. So, yeah, we can be okay with that. P-value is listed as, you know, less than 0.0001, which of course we know is practically zero. So 0 is the best p-value you can possibly have. So we're really good on that front. And height is a genetic trait, so it makes sense that we could use the height of the parents to predict the height of the daughter. So by itself, our model looks pretty good for making predictions. However, it's not the only multiple regression model that we can make. So the question is this really the best model for making predictions? What is the best model for making predictions? Is it the one that we made? Or is there another one we can make that's better than the one that we made? And how do we know that that model's better? Well, let's take a look at that. Here again is our data set. We're going to answer the following questions to determine which model is the best one. So we're using the height of the parents as predictor variables to find out which regression model is the best for making predictions. And we're also going to say why it's the best one for making predictions. Once we have that best model, then we're going to say what's the best estimate of the height of a daughter when the father is 71 inches tall and the mother is 65 inches tall. So we're asked to figure out which model is the best one, and then we're asked to use that best model to make a prediction. So, using the heights of the parents as predictor variables, which regression model is the best for making predictions? Well, this problem, as you saw, does not come with a list of models in tabular form. And some of your problems that you're going to get in your assignment are going to be just like that. If you're not given the models out front in the table, then you have to make that table yourself. So let's go and figure out, okay, how are we going to make that table? We'll start by making 3 columns for your table. So one is for the variables you're going to put into your model. Another is going to be for the p-value. Another is going to be for the adjusted r-squared value. So I can make a table where I label the tops of my columns with those 3 titles: predictor variables, p-value, and adjusted r-squared value. Next, I'm going to put in my predictor variables for my equation. So I can have a model where I'm looking at the father. I have a model where I'm looking at the mother. But I could also have a model where I'm looking at the father and the mother together. So notice I listed each of my predictor variables separately, and then I started looking at combinations of those individual variables. Here we've only got 2 variables, so there's only one possible combination of the 2 variables. So we've only got 3 models that we need to look at. So now here I have my table, and I'm ready to actually start filling it out. And I do that by listing the sample space. So I list each, as I said, I listed each value separately and then possible combinations for those variables. And now I finish my table by making each one of these models and recording the p-value and the adjusted r-squared value for each one. Now, there are assumptions built into StatCrunch, and because of these assumptions, we have to make each one of these models one at a time. There's no special feature where you can actually make each of these models all at once and get a table that we're trying to make from a results window. StatCrunch does not have that capability. So you just have to make each one of these models one at a time and slowly fill the table up and then keep going until you've finished with it. So let's actually do that. Once we put our data into StatCrunch, then we can go to Stat, Regression, Multiple Linear. We're going to get an options window that looks like this. Notice we select, for the first model we're going to make in our table, the predictor variable is the father. So we're going to list the daughter. That's what we want to get out of the model, the height of the daughter. And then what goes into the model is the height of the father. That's just the first model that we're making. Only the father is the only variable, so we're going to select only the father. Once we do that, then we don't have to worry about any of the default settings here in StatCrunch. The default settings are right there for what you need. So once you select your data to make the model, go ahead and click Compute, and then out comes a results window with information like this. So now we've got what we need to actually fill in our table. So we can grab our p-value and our adjusted r-squared value right from the results window. Remember to take the p-value from the ANOVA table. So that's going to go here in our table, 0.175. And then the summary of fits section, the adjusted r-squared value is the one on the bottom. Remember, you don't want plain r-squared, you want adjusted r-squared, because this accounts for different number of variables in your model and different sample sizes. We don't have different sample sizes between these models, but we do have a difference in the number of variables. There's two models that have one variable and one model that has two variables. So in order to make a more even comparison, we want the adjusted r-squared value. So we're going to take this number, 0.0497, and put that into our table. So now we've got the values we need for the first model. Now what we're going to do is we're actually going to repeat that process for each of the other two models in our table. So we just keep going until we're done with all the models. So now we have a complete table, and now we can go back to that comparison method that we saw earlier for comparing which of these models is the best. The last two models have the best p-value. It's a value of 0. So the first model that has a predictor variable of only the father, we're going to eliminate this model because its p-value is higher than the other two. The other two are 0. Here we've actually got something, 0.175. Notice its adjusted r-squared value is considerably lower than the adjusted r-squared values for the other models, so we shouldn't have any problem whatsoever. Just eliminate this model from the get-go. Now we've got two models left to choose from. So looking at the adjusted r-squared values for those two models, since the p-values are the same, we're going to look at the adjusted r-squared values for each of those models, and we notice that they're about the same. I mean, 0.62, 0.63, not a whole lot of difference there. They're pretty much in the same neighborhood. So the only variable left by which to judge the quote-unquote best model is complexity, the number of variables in the model. So here, we're going to take the model for the mother because it has one variable, whereas the model for the father and the mother has two variables. Simpler is better. So we're going to take that model for the mother, and that's going to be the one that we say is the best model for predicting the height of the daughter. Now we can find the regression equation for this model and use it to make predictions. So going back to the results window, when you make this particular model, you get something that looks like this. And notice our regression equation is right here at the top. So the height of the daughter is equal to 16.8436 plus 0.7363 times the height of the mother. It makes sense that we would look at the height of the mother as being a good predictor variable for the height of the daughter. Okay, the height of the female parent is predicting the height of the female child. That actually makes sense. So here we have our model for making the prediction. This is the best model that we can make. It provides the best balance between a low p-value, high adjusted R-squared value, and the fewest number of variables. Now, the second question we were asked is, what is the best estimate of the height of a daughter whose father is 71 inches tall and whose mother is 65 inches tall? Something about that doesn't look right. Maybe it's just me with the something in that the text of that question doesn't look right to me. But that's the question. So let's go ahead and answer it. We have our best model. So let's go ahead. We're given father height of 71 inches, mother's height of 65 inches. Well, we're given more information than we actually need, right? We know the regression equation for the best model, so we can use it to make our prediction. Here's our regression equation. Notice the height of the father is not here, so we were given more information than we needed. I'm just going to put the height of the mother in, 65, punch that out on my calculator, and I get 64.7. This is the height of the daughter, as predicted by our regression model. This leads us into the example of dummy variables. So, many applications involve a dichotomous variable. So there's only two possible discrete values that come out of it. Male, female, dead or alive. Notice this is categorical data. So the way we can actually make multiple regression models with categorical data when there's only two possible outcomes. So if there's only two categories in your data set, you can transform your categorical data into quantitative data by using dummy variables. And the way we do this is we represent one of those values of categorical data with a 0, the other one with a 1. So 0 often represents failure, 1 represents success. So, if you're looking at, say, like you're making a model for the insurance industry, and you want to look at, okay, so we're making a model for life insurance, let's say. So you can use a dummy variable to say, okay, so proportion, this person's dead, this person's alive. So you could say that the dead is a 0 and the 1 represents the alive. Or you could actually switch it up, because if you're making a model for insurance, you want the 1 to represent the success. You actually, you can actually flip it up and do it the other way, because you only pay out when people are dead. Okay, so the success could be considered, when you actually pay money out. Although if you are in the insurance industry, success for you is going to be when you don't pay the money out. So maybe the 1 represents the people being alive still, and the 0 represents the dead. Anyway, you can do it either way. It doesn't matter. You just have to remember which way you set it up, because that's the way you set it up is the way that you have to use the model. So this is what we call a dummy variable, where we only have two values like 0 and 1 going on in the model. We can go back to our example of the height of the daughter given the height of the parent, but we extend that to the height of the son as well as the daughter. So we're looking at the height of a child, and the child could be female or male. So we just assign a 0 and a 1 to each of the different genders, and then we use the randomly selected data to construct our model. So we make the model in StatCrunch, and we find out that our best multiple regression model is the one that you see here. So we have the height of the child, the mother, and the father. And the gender of the child becomes a part of the actual model itself. So we got 3 predictor variables producing 1 response variable. Again, we get that from the top of the results window that comes out of StatCrunch. Notice that the parameters for the model are the same ones that are listed here in the parameter table. So sometimes it's easier, especially when you're typing your coefficients into those little fields for your assignments. Sometimes it's easier to just get the coefficient from your parameters table than it is from looking at this whole, hunk of characters right up here. Sometimes it's easier to actually see them here in the parameters table. And if that's the case for you, as it is for me, that's how I do it, go ahead and feel free to do that. Either way, just make sure you put the right number in for your answer. So we find that using this model, when we have a mother that's 63 inches tall and a father that's 69 inches tall, a daughter will be predicted to be 62.8 inches tall. Where does that come from? Well, that comes from using our regression model. So here we have the regression model where we substituted in 63 for the height of the mother, 69 for the height of the father, and then we set this up to where 0 is the gender variable for the female. So since we're predicting the height of a daughter, the value for gender is 0. So we punch this out in our calculator, and that gives us 62.806, or 62.8 rounded to 1 decimal place. If we can use the same two parents, but we're making a prediction for the son, then that child will be predicted to be 67 inches tall. Again, we're going to put in the values into our regression model. So again, the same values for the mother and the father, but this time we put in a 1 for the gender to represent the son, because we set this up to where 0 is female and 1 is male. So we're predicting for a son, therefore we put 1 in for the gender, and we punch that out on our calculator and get 66.956, or 67.0 rounded to 1 decimal place. And that's really all there is to it. That brings us to the end of this lecture. If you have any questions, you know what to do. Otherwise, I will see you in class or the next video. Thanks for watching.